Cracks yesterday evening in a spectacular fire. Witnesses likened it to an atomic blast with a characteristic mushroom cloud. Earth tremors were felt more than 30 miles away. 6 persons were injured in the fire, which caused more than $1 million in damages. Firefighters from 9 surrounding
Fire at a gas terminal near here, killing 2 men and injuring 3 others, has been blamed on a malfunctioning refrigeration unit. Those on the scene reported flames roaring 150 feet in the air and debris flying in all directions. However, the flames did not reach several nearby tanks containing chemicals. They were killed. $100,000 in damage was caused because a truck backfired. The truck had just been filled with gasoline from the bulk storage tanks behind it and was pulling away when it reportedly ignited fuel spilled on the ground. When it was over, all 5 gasoline and diesel storage tanks were destroyed. Fortunately, no one was reported injured in the
Been here for the past 2 hours trying to contain the blaze. It's so widespread that major efforts are concentrated only where they're most needed. And although the fire appears to be nearly under control, firefighters say anything can still happen. It's not out yet, so we'll keep you posted on any major developments.
What do all these reports have in common? They all involve storage tanks or containers that were closed. Containers in a position to rupture when heated by a fire. A container can be of any size or any shape, can contain almost any kind of material, liquid or gas, flammable or non-flammable, and it can be in any kind of environment. But in a fire, the fact that a container is closed makes it dangerous. There are 2 general classes of closed containers. The first is the ordinary container. It can be of any shape or any size. Its primary use is to hold liquids and their vapors under normal temperatures and pressures. However, some volatile liquids exert enough pressure at normal temperatures that they would overstress an ordinary container. These liquids and other materials, which are normally a gas, require a second class of closed container, the pressure container. It's a stronger, specially designed container characterized by its rounded ends, and it usually has a safety device for relieving excess pressure. At first glance, the pressure container and the ordinary container appear different, and in many respects they are different. But in the heat of a fire, they both behave as pressurized containers. This is what happens. As the temperature in a closed container rises due to excessive heat, molecular activity increases and the liquid begins to boil and vaporize into gas. As a result, the gas exerts more pressure against all the internal surfaces of the container. As heat is added, boiling continues to increase the pressure, but the boiling may begin to slow as pressure and temperature begin to reach a balance point. Ordinary containers are not designed to hold the increased pressure and will eventually rupture. What are the warning signs that pressure is building up in an ordinary container? One sure sign is the rounding out of any flat surfaces such as the end. The round shape more equally distributes the added stress. As the ordinary container rounds out and the flat areas are stressed, a metallic pinging noise may be heard. As internal pressure increases, the areas under greatest stress will give out first. This generally occurs near the seams at either end of the container. Depending on the amount of heat applied and any weakness in the material, the container may rupture. The extent of the rupture may vary. A small area of the container may crack open and vent. In such a venting, the height of the flame and its sound will give clues to the amount of internal pressure involved. The lower or higher the flame, the lower or higher the internal pressure. The same can be said for the sound it makes. The lower or higher the pitch, the lower or higher the pressure. Just as pressure will rise when heat is applied to a liquid, pressure will fall when it's cooled, reducing the height of the flame and lowering the pitch of the sound. When a container has only partially ruptured, the pressure is only partially released. If the flames around it are hot enough to build up enough internal pressure, it may rupture completely or explode, releasing all the pressure at one time. This is not an explosion due to internal combustion, but rather an explosion due to the pressure behind the expanding vapor. When such a container holds any amount of liquid at a high temperature, the sudden boiling of that liquid may add to the force behind the expanding vapor. This is called a BLEVE, a boiling liquid expanding vapor explosion. Here's how a BLEVE develops. All liquids have a normal boiling point at atmospheric pressure. As the pressure in a container rises, the boiling point of the liquid also rises. The pressure limits boiling, even though the liquid may be at a temperature well above its normal boiling point. When such a container bursts and the pressure suddenly drops, the liquid vaporizes with explosive force. If the vapor is flammable, it may be ignited by the surrounding flames. This is the characteristic fireball, scorching everything and everyone within its area, and perhaps starting new fires. In analyzing this same explosion, note where the vapors are ignited. At the start of the burst, the vapor expansion is so violent that it extinguishes the surrounding fire. Once the vapor is mixed with air, it can be ignited by an outside source. The flames then follow the expanding vapor front until it is entirely consumed. This is the most dangerous type of closed container rupture, when flammable liquids and their vapors are involved. Many liquids in closed containers are not flammable. This does not mean they won't burst or BLEVE. Even though the expanding vapor may not ignite, a real danger is present from flying debris. Large objects can carry further from the explosion than the expanding vapor and in any direction. This barrel took off at a speed of 200 feet per second, yet it burst at an internal pressure of only 75 pounds per square inch. As an ordinary container, it was not designed for that pressure. On the other hand, pressure containers are usually designed to withstand internal pressures of 100 psi or more. To withstand these higher pressures, they are designed with rounded corners and ends. And they generally have some type of relief device to vent off excess pressure. Here's how a relief valve works in a fire situation. When the internal pressure of a container reaches the point at which the relief valve is set to operate, it will open to relieve the pressure. The pressure then begins to drop, and the boiling increases. On some smaller pressure containers, the relief valve will pop out and vent continuously until the internal pressure is equalized with atmospheric pressure. On larger tanks, when the internal pressure falls below the relief valve setting, the valve will close until the pressure builds up again. As long as the relief valve is operating properly, the internal pressure will be controlled. A working relief valve will vent at intervals. The length of each interval depends on the amount of heat being applied to the container. The shorter the interval between each venting, the more heat is being applied. Also, the more heat applied, the longer the period of venting. During intermittent venting, the height of the flame should stay relatively constant. If enough heat is applied, venting may be continuous, indicating that the internal pressure is building as fast as it is being relieved. In this case, as with ordinary containers, the flame height and its sound can be clues as to the amount of heat applied. In either case, the relief valve should keep pressure from rising beyond the design strength of the container. But a relief valve alone is not enough to keep a container from rupturing. It may still blow. Flames impinging on a container may weaken it enough for it to burst, and this can occur at any time, even before the relief valve vents. Of critical importance is whether the flame impinges above or below the level of the liquid inside the container. When flames impinge below the liquid level, the liquid absorbs much of the heat. But flames hitting above the liquid level rapidly raise the temperature of that part of the container. Most closed containers are made of some kind of metal, usually steel. When the temperature of ordinary steel is raised high enough, it loses all its strength. Under sufficient tension, steel will begin to stretch at somewhat lower temperatures. It stretches and eventually breaks. With a combination of high temperature weakening the metal above the liquid level and increasing pressures, any container will bulge and eventually rupture even before the metal is hot enough to glow. Again, as with ordinary containers, pressure containers may merely crack open and vent. The height of the flame and the pitch of the sound will give clues to the amount of pressure involved. Most pressure containers, when heated sufficiently, will burst open rather than vent. The destructive force of an expanding vapor explosion can be great. This LP tank contained only a small amount of liquid before it was torn open. The combination of high internal pressure and the external weakening of the metal above the liquid level caused this bulging and tearing. All pressure containers, regardless of their size, are subject to these same forces, causing them to bulge and tear apart in random fashion. In this situation, several liquid propane tank cars have exploded. When they ruptured, the prime dangers were from heat and from flying debris. In all situations, chief officers must make operational decisions, and firefighters need to know how to minimize their risk in doing what's necessary. In fighting such a fire, the prime safety factor is distance. Relative safety increases as the square of the distance from the fire. For example, here at 100 feet from the center of the fire, a firefighter would have been in extreme danger. At 500 feet, or 5 times further away, his relative safety would be 5 squared, or 25 times greater. At 1,000 feet, or 10 times the original distance away, his relative safety would be 10 squared, or 100 times greater. In any closed container fire, distance is your greatest ally. The further away you are, the safer you are. Also, the less time you spend close to such a fire, the safer you are. The exact moment when a container will burst cannot be predicted, and if you are close when it blows, there is no time to escape. Your only hope then is your personal protective gear. But this doesn't mean that some control measures can't be taken to stabilize the situation with a minimum of risk. Deluge guns or automatic water distribution appliances may be set up under cover of hand lines. This allows continuous cooling with short-term exposure to personnel. If such appliances aren't readily available, makeshift methods can also serve the same purpose. In sizing up a situation, two primary questions arise. What dangers should firefighters be exposed to? And how can each firefighter minimize the risk? Decisions involving the degree of risk must be based on the importance of the mission. For example, are other lives in danger to justify going in? If little is to be gained, then little should be risked. The answer to the second question, how can a firefighter minimize the risk, is based on what is known about how closed containers may react in a particular situation. The likelihood of unanticipated occurrences in closed container fires emphasizes the need for full protective clothing, backup lines, the use of natural barriers for shielding, and positive communication. Any decision that is made or action taken should be based on a continuous exchange of data gathered from all sources. This means careful observation by everyone, using both eyes and ears. Watch for the effects of flame impingement. Sometimes a fire burns so cleanly that it has no color and is difficult to see. So look for the effects of the flames: flaking paint, bulging, or a dull glow of the metal. Also look for venting, either through a relief valve or through a partial rupture in the container. Since the venting may not be ignited in some cases, you should also listen. Listen for the roar of venting pressure and for the pinging sounds of a container rounding out. These clues not only indicate the possible danger, but also can indicate how effective your control measures are. You should be aware of these clues in any fire, because a closed container can be in any fire. If you know what's happening, you'll have a better idea of how close to go. If you don't know, then don't go. It may blow.